In this video, we're going to take a look at Target 24, writing equations for transformed parent graphs. What that means is graphs of our regular shapes, parabolas, cubics, whatever, are moved around the graph paper. The key to this strategy is having your parent graph toolkit sheet of notes out in front of you. This sheet of notes is really important because it explains all of the formulas and equations that we've been doing for each type of graph. So whether it's a parabola that gets moved, this is the big equation. If it's a cubic that gets moved, it's this one. If it's a hyperbola, you have to know the intersection of the asymptotes, and then we use this one. If we do an exponential, we need to know one point on the asymptote, and then the distance up to the point on the graph is the a value. And then we've done sleeping parabolas, where their equation includes a square root, and then absolute values, which have absolute value bars and make a v. And then we've also done circles, which look like this. So this sheet of notes obviously is pretty important in order for you to really be able to attack these type of problems and know exactly what you're doing. So when you look at these, you determine the shape, and then you determine the formula you're using from your notes sheet. So here, I know that I'm doing a parabola, and the parabola is at over 2 up 3. That's the key point. It's called the locator point. And then I know I'm going to be using my equation y equals a times x minus h squared plus k, and the vertex is always your h and k. So these numbers right here are going to go in for your h and your k. And then the a value on this, we can assume that it's 1 unless we're told differently or we're asked to make that calculation. And at this point, we're just writing the equations of transformed graphs. So all we have to simply do is say, okay, it would be x minus, 2. That needs to be a 2 because we're replacing the h with a 2. So I'll make sure I put a 2 there. And then I'm going to square that, and then plus 3 because it's kicked up 3 values. And it's as simple as that. That's the equation for that parabola. Now you look at this shape, it's a different shape. It's a cubic. It's that S kind of curve. Well, it's at the same point. Its vertex is at, its locator point is at 2, 3. So then I'm going to end up just using the formula for that. The only difference between a cubic formula and a parabola formula is that instead of being to the second power, it's to the third power. So it is a really pretty simple equation to know. It's just a third power equation instead of second. So then you get y equals, and the a value we're going to assume is 1, the stretch value is 1, and so then it's x minus 2 cubed plus 3. And that would be the equation. And then this guy, the things to consider are that this parabola opens down. So it's going to have a negative because it's opening down. So if I'm going to do that one, then let's kind of move it down here into some open space. It would be y equals a negative number. So I'm going to say negative 1 times x plus 6 because it's moved left. And we know that it's kind of that opposite thinking. And then it's squared, and then be plus 0 because there is no kick value. It's not kicked up or down. Now we don't usually write the plus 0 on the end. That doesn't really make a lot of sense. So the answer would just be negative x plus 6 squared. And that's what it would look like. I would like to continue with some of the harder ones. People think hyperbolas are difficult. It's really not that bad because once I know the point that the asymptotes intersect, so in this case, if this is my origin, I'd go back 1, back 2, back 3, and then down 4. So this is negative 3, negative 4 as the intersection of the asymptotes, and then that becomes our locator point. So the equation for a hyperbola, because this is two curves, it's a high 5 that misses, is y equals a times 1 over x minus h, and then plus k out here. Well, if that's the intersection of the asymptotes, that's my h, that's my k, I just plug them in. So we just go y equals, and then this is a regular one because we have a curve in the upper right. It's not a negative, it's not an upside down because of the high 5 that misses in the upper right. So when I do my hands, they curve and miss each other. Then upper right is fine. And then so then I would have 1 over x plus 3 because that was minus 3. This would be plus because it's a subtraction-based equation. And then minus 4 would be the number on the outside of that fraction and sitting next to us to get us down to negative 4. On an exponential curve, you need to know one point on the graph, and you need to know how far away that point is, or excuse me, you need to know one point on the asymptote, and then you need to know how far away that point is from the graph itself. and here I can see it's exactly 1 point away. That makes my a value equal 1. Now remember, exponential curves are based on y equals a times b to the x minus h power and then plus k, which would look like that. So now this is my over 4 up 2, so 4 comma 2 are my h and k again. So y would equal, a value we decided was 1, and then my b is a multiplier. We usually just pick 2. You could pick 3. It doesn't. You just need to put a number there for a b value, and then it would be to the x minus 4 power, and then it's kicked up 2, so it'd be plus 2 up there. So that's how you do the exponentials as well. The key to this strategy is finding the locator point and using your notes page to pick the right equation.